In this video, we're going to investigate what's known as the logistic growth model. But before we get started on this new concept, there are a few useful pieces of prior knowledge that you should have before you start on this lesson. And the first is the idea of uninhibited exponential growth or decay. And this is another model that you would investigate in most calculus courses, where we have the rate of change of some quantity with respect to time being directly proportional to the quantity itself. And the solution to that differential equation is the quantity at any given time is equal to some constant times e to the kt, where k is a proportionality constant and c is generally the initial amount that you have at time 0. The second piece of knowledge you should have is the idea of inhibited growth or decay. And in this model, the rate of change of some quantity with respect to time is directly proportional to that quantity minus some constant quantity that we'll call m. And this m just acts as an upper or lower boundary to how high or how low that quantity can get. And the solution to that differential equation is our quantity at any time equals some constant times e to the kt plus m. And the third piece of knowledge you should be armed with is how to complete a partial fraction decomposition. And that's the idea of taking some fraction, like 1 over x squared plus 3x plus 2, where the denominator can be factored, in this case into x plus 2 times x plus 1, and it's the idea that we can decompose that into the sum of two different fractions, where each denominator is one of those factors. And the big question behind everything in this video is how would you describe the way a population, say of animals, humans, viruses, anything that experiences exponential growth, how would you describe the way that type of population grows? Well, one idea is that maybe it experiences uninhibited exponential growth or decay, a situation that visually looks like this. But there's an issue here in that nothing can truly grow exponentially. None of the things we've discussed can grow infinitely large due to the strain on resources and the environment around them. So maybe then, if there's going to be some sort of limit to how something grows, we would think of the inhibited growth or decay model, where visually for growth, we'd see something like this: an amount that starts very small, grows big quickly, and then levels off. Well, the asymptote at the top, to force the population to level off, that's a nice component for us to have. There's still an issue with this model in that it looks like the fastest growth occurs at the very beginning for the population, when the population size is at its smallest. So this model probably also not very realistic. But what if we could solve both those issues at once, using a model that looks like this: flat at the beginning, sharp in the middle, flat at the end. One that would show a population that starts off by growing very slowly, then speeds up, and then slows down as it catches up to the constraints of its environment. This would probably be the most realistic. And this particular model has a name. This is what's known as the logistic growth model. And in the logistic growth model, the rate of change for some population, or even to generalize it, for some quantity, is directly proportional, same wording we saw with the exponential growth and decay models above. The rate is directly proportional to the product of the population itself and the difference between the number 1 and the ratio of the population to what we're going to call the carrying capacity. And the carrying capacity is going to represent the maximum population that is possible, or if this changed to decay, the minimum that's possible. And the model looks like this. The rate of change for population with respect to time equals our proportionality constant k times p times the difference between 1 and the ratio of p over m. And the next part of this video is going to go into solving for the population at any given time, p of t. And step 1 in this process will be a separation of variables, which will yield dp over p times the quantity 1 minus p over m equals k times dt. Now we're going to do one thing to make our calculations easier, and that is multiplying the fraction on the left by m over m to yield m over p times the quantity m minus p dp. I got that fraction by distributing the m in the denominator to what was inside the parentheses. Our next step will be to integrate both sides, but for that fraction on the left, we're going to need a partial fraction decomposition, which goes back to the prior knowledge I mentioned earlier. Now, I'm not going to show all the steps to this decomposition, I'm only going to show you the end result, that fraction would separate into 1 over p plus 1 over m minus p. I leave proving that to you if you really care about it. And this will still equal k times dt. And now we can integrate both sides. On the left side, just be careful. Both of these look like they will integrate using the natural log, but think u substitution. If I set the denominator on the second fraction to be u equals m minus p, du would be a negative dp, which means our first fraction will nicely integrate to natural log of p, but the second one will be a negative natural log of m minus p. And on the right side, we will get k times t plus our constant c. Using properties of logarithms, we can condense the left side into natural log of the quantity p over m minus p and leave that equal to kt plus c. Now, just like we did earlier, we're going to take an extra step for ease of future calculations in this problem. And what we're going to do is multiply both sides of the equation by a negative 1. So that on the left side, we'll add a negative in front of that natural log, we'll add another negative in front of the k. We won't worry about a negative in front of the c because negative of a constant is still a constant. And the purpose for this is to insert that negative 1 into the natural log as an exponent and create the natural log of the quantity p over m minus p being raised to the negative first power, equal to negative kt plus c. And this allows us to flip that fraction and write its reciprocal. The natural log of m minus p over p equals negative kt plus c. And now we'll move to eliminate the natural log on the left side by making both sides powers of e. And this will yield m minus p over p equals our familiar c times e to the negative kt. Note that when t equals 0, that will make e to the negative kt equal to 1, and that c value in front will equal m minus p over p, or more specifically, our carrying capacity minus the initial population, all divided by the initial population. And now we get the purpose of wanting the reciprocal of that fraction from before. We can now rewrite the left side as m divided by p minus 1 equals c times e to the negative kt. Adding 1 to both sides, we'll get m over p equals 1 plus c times e to the negative kt. And by multiplying and dividing in the same step to swap the denominator on the left for the expression on the right, we solve the differential equation to yield that p of t equals m divided by 1 plus c times e to the negative kt, where m is the carrying capacity for the population in the problem, and k is our proportionality constant. And so we'll finish up the video by taking a look at one example to pull everything all together. And the example we'll look at states that in a population of 500 people, 4 of these people are actually zombies. And for the problem, we'll assume that zombie infections follow a logistic growth model. So that means we can model the infections using our differential equation, dp over dt equals k times p times the quantity 1 minus p over m. And specific for our problem, the carrying capacity has to be 500. If there are only 500 people, we can only have 500 zombies. And we'll add one more thing to our problem. We'll say that the constant of proportionality to tie this differential equation together is equal to 1.25, which makes our k value in the problem 1.25. That means our original differential equation can actually be written as dp over dt equals 1.25p times the quantity 1 minus p over 500. Now, a large portion of this video was committed to developing the solution to our differential equation. The solution being that p of t equals m over 1 plus c times e to the negative kt. So if we already know that that's the solution to the differential equation, we don't need to develop it again. We can say that for our problem, the population of zombies at any given time is equal to 500 over 1 plus c times e to the negative 1.25 times t. And since it wasn't noted in the problem, you can note to yourself that t should represent time in days. Now, this would give us a general model for the population at any time, but if we want the true population of zombies at any time, we need to resolve that constant c. And what we know about the problem is our population at day 0 is 4 zombies. And substituting in a population of 4 and a t-value of 0 will yield 4 equals 500 over 1 plus c. Swapping the denominator for the expression on the left will yield 1 plus c equals 500 over 4, so that 1 plus c equals 125, and our c value is 124. So our final model to give the population of zombies at any time will be 500 over 1 plus 124 times e to the negative 1.25t. And that closes this lesson on the third type of exponential growth or decay model, the logistic growth model. Thank you for watching.